Hey everybody, I am doing this video today to show you how to solve resistance total in a series parallel resistive circuit. So as you can see on the board here, I have constructed a parallel resistive circuit. Contained within the circuit, I have purely resistive loads. R1 is represented by 10 ohms, R2 and 3 are 10 and 5 ohms, R4 and 5 are both 5 ohms, R6 is 8 ohms. So I want to now start to take this circuit and break it down to solve for resistance total. In order to do that, you need to understand which resistors are directly in series with each other and which resistors are directly in parallel. To begin with here, I want everyone to recognize that resistor 2 and 3 are directly in parallel. So the load side of resistor 2 is directly connected to the line side of resistor 3, providing only one path. That would constitute to resistor 2 and 3 sharing the same value of current, which also is a factor in a series circuit. The same would be true for resistors 4 and 5. They are directly in series with each other, being that the load side of resistor 4 is directly connected to the line side of resistor 5, providing only one path for current flow. So in order for me to condense resistor 2 and 3, I simply would add them together. So resistor 2, 3 is added directly. So 10 ohms plus 5 ohms gives me a resistance of 15 ohms. I'm going to do the same thing for the other branch of the circuit. R4, 5 would be additive. So 5 ohms plus 5 ohms. And that would give me a resistance of 10 ohms. So now that I have taken the resistors that are directly in series and condensed them, I am going to redraw the circuit. So when you're finding the resistance total of a series parallel resistive circuit, it's all about reduction and reduction in the correct order until we end up with a series circuit. So R1 will be brought down exactly as shown. My R23 now has been brought together. My R34 has been brought together. So I will redraw it in that manner. And then resistor 6 is untouched. Okay, so resistor 1 is still 10 ohms. Resistor 2, 3 has been condensed to give me a resistance value now of 15 ohms. Resistor 4, 5 likewise has been condensed to give me a resistance of 10 ohms. And oh, R6, I didn't give you R7. Sorry about that. R7 was 10 ohms in the original. Okay. And that looks like that. So R6 is 8 ohms and R7 is 10 ohms. So the first step being take all resistors directly in series with each other and condense them. So that's what I have done in the second drawing of the circuit. So now I no longer have resistors directly in series. Resistor 1 is in series with the parallel branch of R2, 3, and R4, 5. However, I am unable to further add them together because the parallel branch needs to be reduced. Same being said for the R6 and R7. To reduce that further. So that will be the next step for solving the resistance total of this circuit. So R23 at 15 ohms is directly parallel with resistor R45 of 10 ohms. Electrically, this point of potential is the same as this point of potential. So whatever volt drop you would read across resistor 2, 3 would be the same value of volt drop that you would read across resistor 4, 5. This constitutes a parallel circuit. So to reduce that further, we must add the resistor 2,3 to resistor 4,5 using the reciprocal method. So I'm going to rename resistor 2,3, resistor 4,5 to Rx just for simplification purposes. So for me to solve now for Rx, I have to add those resistors reciprocally. And the formula for that looks like this. So Rx equals 1 all over 15 ohms plus 1 all over 10 ohms. So when you put this into your calculator, you come up with Rx equals 6 ohms. And it's always true to say that the resistance total of a parallel branch will be smaller than any branch contained within the circuit. So R45 was 10 ohms. My resistance total for that particular branch is 6 ohms. So we have satisfied that rule. So I am going to now move into solving and reducing R6 and R7. So R6, 7 equals, again, electrically this point is shared, this point is shared. So if you were to read the voltage value across resistor 6, it would equal the same value of voltage across resistor 7, concluding that this is in fact a directly parallel portion of this circuit. So I am going to add those resistors together using the reciprocal formula yet again. Okay, so 1 all over R6 plus 1 all over R7, which equals 1 all over 8 ohms plus 1 all over 10 ohms. When you put that into your calculator, you come up with a resistance value of 4.44 ohms. So now I'm going to take the time to redraw the circuit. So now I'm going to take the values that we've calculated using a reciprocal method, breaking the parallel branches down further, giving us a redrawn circuit that's going to look like this. So again, resistor 1 is unchanged. We took resistor 2,3, reciprocally added it to resistor 4,5 and calculated and renamed Rx to be 6 ohms. Okay, so that's reduced. And using the reciprocal method, we did the same thing to resistor 6 and 7. Adding them reciprocally, we took our 6 and 7 and calculated a resistance of 4.4 ohms, further reduced. So resistor 1 is 10 ohms. Resistor 2,3 added reciprocally to 4,5, we renamed to be Rx with a value of 6 ohms. Resistor 6, 7 reciprocally added together, we renamed R6, 7 with a resistance of 4.44 ohms. So at this stage in the circuit, we are left with 3 resistors that are wired together in series. Therefore, we are now able to get our resistance total simply by adding these values of resistances together. So resistance total in a series circuit is additive. So resistance total equals R1 plus Rx plus R6, 7. So R1 is 10 ohms plus Rx is 6 ohms and R6, 7 is 4.44 ohms, giving us a resistance total of 20.44 ohms. In my next video, I'm going to further take this circuit and show you how Kirchhoff's current law and Kirchhoff's voltage law applies to a series parallel circuit. So please make sure you view that video to get the further details of this specific circuit. Thank you.